Now we are going to talk about the frequency response of negative feedback systems. So we have our equation here for the asymptotic model. So we have the gain as a function of the asymptotic gain and the loop gain. Okay, but if we replace these factors as their Laplace transforms, so we have that these are basically complex numbers over frequency, so we can expand this. So we have the first term, the asymptotic gain, assuming that the amplifier is ideal. It can be represented with a DC level, and then the DC level is going to be like this. 0, because it is a 0 Hertz, so we take this 0 Hertz. And then there will be a number of zeros and a number of poles. Okay, so we will have this transfer function. So we will call this product of zeros and product of poles N asymptotic gain and D asymptotic gain. So this will be all the product of the zeros, and this will be all the product of the poles. Okay, we will do the same for the loop gain A beta. A beta, there will be a component that is DC, and there may be a number of zeros and a number of poles. So the zeros we will call the numerator of AB, and the poles we will call the denominator of AB. Okay, so then when we take these equations and then plug in our equation for the asymptotic gain model, we have a rather large equation when we expand it, and then we're going to go term by term here. First, we have, as we expect, a term at DC, frequency 0, that depends only on the asymptotic gain. Okay, then we will have a term that depends also, that it is also a DC, frequency 0. This term depends only on the low frequency gain of the amplifier and on beta, the feedback components. And this one, we can see that it is always going to be always lower than 1. It approaches 1 only when A beta null it is very, very large. Okay, so that is what we will call the accuracy of our system. And then we have the frequency dependent part, that is the poles and the zeros, and we will have that we have the numerator of the asymptotic gain coming directly here, denominator of the asymptotic gain, and then there will be a product of something very interesting here. We have the numerator of the loop gain divided by this part here. So this part is the denominator of the loop gain that appears divided by the loop gain here. So the loop gain, it is basically affecting this denominator, the value of this. And then we have also the numerator of AB, that it is multiplied by this factor. So we have poles and zeros in this transfer function. The main interesting thing that we have here is that they are going to be affected by the gain. They are going to be moving. Now there is some very interesting observation that we can make here. And it is that, as we talked before, the asymptotic gain is equal to 1 minus 1 divided by beta. We can see that a pole that appears in the asymptotic gain actually becomes a 0 in the loop gain because this term appears here. So when we invert it, the pole becomes a 0. So we will explain this one a little bit better because it is extremely important. So let's take back our example. We have a plus, minus, we have resistor 1, resistor 2, and actually I will put resistor 2 here, and I will add a capacitor here. We'll add a capacitor. This is V in, this is V out, and this has an amplification A. So if we assume that the amplification A is infinite, and we calculate the asymptotic gain, that is the assumption that we have an ideal amplifier, then we see that we can calculate the gain as the following: E omega C, and this divided by R1, and then this will be equal to R1 plus that will be R2 divided by 1 plus G omega R2C divided by R1. And then if we continue this, this will be R1 1 plus G omega R2C plus R2, and all these things divided by R1 times 1 plus G omega R2C. Okay, and then we continue working with this. That will be R1 plus R2 plus, that will be G omega R1 R2C, and this the denominator is already in both the normal form, so I don't need to change it. Omega R2C. Then I multiply this by R1 plus R2 and divided by R1 plus R2, so it doesn't change. That will allow me to factor R1 and R2. That will give me R1 plus R2 divided by R1 times, and that will be 1 plus G omega R1 R2 divided by R1 plus R2, that is a parallel combination, times C, and then 1 plus G omega R2C. Also that will be equal to the DC part. We expected R1 R2 divided by R1. It only depends on the resistors. There is 1 0, 1 plus G omega, that will be R1 in parallel to R2C, and then we have one pole that it is located at 1 plus 1 G omega R2C. Okay, So this is our asymptotic gain, and then we see that it has a pole here, single pole. This is the pole in the asymptotic gain. Now let's try to find the loop gain beta, and then this is probably the last time in this course that I'm going to break the loop of the amplifier, because as I mentioned before, we typically don't do this due to loading reasons, but it is just a little bit easier to explain. So I'm going to break the loop here, R1, this is R2, and then we have the capacitance here, and then I will call this node Vx. This will be V in and V out. So the total loop gain, I can calculate the total loop gain A0 beta if I calculate this transfer function in this direction. Okay, so this transfer function A beta will be equal to A, that is the transfer function from the input to the output, and then we have a voltage divider here, time R1 divided by R1 plus R2, that it is in parallel to 1 over G omega C. Okay, now I'm not going to do this again. If you see, this part looks exactly the same as this part, but it is inverted. Okay, they are exactly the same but inverted. So the same result that I have it here for the asymptotic gain will be also for the loop gain, but inverted. So I will have R1 plus R2 divided by that will be R1 divided by R1 plus R2, and then the pole will become 0. That means that this pole will appear here, R2C, and then the 0 will become a pole, omega R1 in parallel to R2C. Okay. So we see that a pole in the asymptotic gain gets transformed in a 0 in the loop gain, and this has very profound implications in what we are going to do right now. So we come back to our equations here. So we have demonstrated with an example that a pole present in the ideal asymptotic gain becomes a 0 in the loop gain. So if there are no other zeros in the loop gain, then what we can do is we can simplify this equation a little bit. So this is the zeros, the 0 in the loop gain, this one, and the pole in the asymptotic gain, they just get simplified. Okay, they get simplified, and then the new equation looks like this. We have that the part that depends on the frequency, we have the numerator of the asymptotic gain, and then we have the position of the poles. The poles look like this. We have that the denominator of the loop gain is affected by the DC loop gain, that it is here. And we have also that the zeros, this is the 0 of 0 of AB of the loop gain, the 0 of AB appears also in the denominator, and modify the position of the poles. And this is something interesting because we really don't see the 0 here in the equation, but it is affecting the position of the poles. Since we don't see it, we call it a phantom. It is a phantom 0. We will see very soon that we can use this for many interesting things. So let's take a first example. So let's assume that we have a system that has a single pole. Okay, the pole is going to be located at 1 kilohertz. We can actually draw the transfer function as a frequency. So we have the frequency here, we have the transfer function here, and then the gain will be 20. That will be 20 is equal to 26 decibels. 26 decibels. It's going to be located here, A0, and then there is a pole at 1 kilohertz. So this will be 1 kilohertz. So we have one pole going like this. Okay, so we have this gain, and then we're going to assume that our system has a beta equal to 1. And then there is only a beta at low frequency. There is no zeros or poles in the beta transfer function, so it is ideal. It is only 1. So what happens when we have this system? So we can put our system as we have it here. Mathematically, the gain will be A0 divided by 1 minus SP1. That is a bottom normal form. And then A beta 0 will be the low frequency gain, 20 times the beta, that will be minus 20. And then the total, the resulting gain, the closed loop gain, AT, will be equal to, and then we have the asymptotic gain multiplied by A beta minus, divided by minus 1 minus A beta 0. Okay, and then we have everything that we need for this. So the total asymptotic gain, it is equal to 1 over beta, that will be equal to 1, minus beta, that will be equal to 1. Okay, so when we solve this equation, with the pole, we have that we replace A here and A here, but the following expression that we have, we will see that we have the following equation. The low frequency part has not changed. This depends only on the C. This has not changed, we expected. But the position of the pole has changed, and has changed a lot. The position of the pole has been moved the same amount of the loop gain, A beta 0. So originally the pole was here in P1, but now it has been multiplied by 1 plus A beta 0. So this is something very interesting. So if it started in 1 kilohertz and then I put feedback, suddenly this is going to move towards the right to a higher frequency. So how does it work? Let's take a look in MATLAB an example. So I have the following scripts in MATLAB, okay, so that we can use to explain how the poles and zeros affect the negative feedback. So we are going to test now the first example. The first example, it is no zero in AB and a single pole. So we have a single pole, and then we're going to run our simulation. And then what we see is that our pole, original pole, that is at 1 kilohertz, when I start adding loop gain from 0 to the value that we have in the example 20, in small steps we see that it starts moving slowly. So the loop gain in this case it is 20, A beta is equal to 20, minus 20. So according to our equation, it should move to 1 kilohertz times 1 minus the loop gain, so it should move to minus 21 kilohertz. So we see that when it ends up here. So it starts here in 1, and then it stops in minus 21 kilohertz. So when I plot the trajectory from the original position of the pole without closing the loop, and then I start increasing the gain to my final loop gain, we call this plot the root locus, and then there is in MATLAB a function that calculates the root locus and do it yourself. Yeah. So the starting one, and then it goes to a higher frequency, to 21 kilohertz. So we can see here that this value was 20. We put a loop gain of 20. So this was minus 20. Multiplied by minus, here it gets plus 1, P1. So the pole get moved from 1 kilohertz here. So this was 1 kilohertz. It got moved to minus 21 kilohertz. So increase the bandwidth. It has the loop gain has moved the bandwidth here. So this is the first conclusion that we have. Is a real pole that has been moved to a higher frequency. Now, what happens when we have a negative feedback with 2 poles? Yeah. So we have the same example, but we have added a second pole, and then our transfer function for our amplifier will be A0, that it is 20, that is our gain at low frequencies. Then we have the 2 poles here. We keep A0, beta 0 equal to minus 20, that is that beta will be equal to minus 1. So beta equal to minus 1. And this is here, and no zeros involved in this example, just poles. So when we calculate the closed loop gain, we replace A and A by the transfer function, and then we have something a little bit larger here. And at very low frequencies, this shouldn't change, it is exactly the same. But now we have something interesting. We have a part that it is DC here on the top. And then in the denominator we have a frequency dependent equation as a Laplace with Laplace variable, and this is a second order equation. A second order equation can have the roots of the second order equation can be the real or complex, and if they are real or complex, it will pretty much depend on the position of the poles and also on the factor 1 plus A beta 0, on the loop gain that I have. This is an extremely interesting result because the amount of feedback that I put, the amount of loop gain feedback that I put is going to manipulate the position of the poles. So let's run our examples in MATLAB. Let's see, we add a second pole to this system. Let's see what happens. So we have a single pole. We are going to comment this. Now we are going to add a second pole. We run the simulation. And then what we see is that the original positions of the poles were here, and then when we start increasing the loop gain, first they get together, they crash somewhere around 3 kHz, and then they split, become complex. And they go vertical. So this is the behavior of two-pole system without zeros. And I am continuing augmenting the gain. At some point when we arrive to the loop gain that it is the one that I apply in my circuit, we will see the resting points of the circuit. So we have that the final positions of the poles are here. So they became complex poles. We can see the root locus also, they give exactly the same result. The origin of the poles is here. We increase the gain. At some point it splits here at 3, and then they become complex poles. One goes up, the other goes down at the same distances. Now let's add a third pole. Let's see what happens. So I have added a third pole at minus 15 kHz. I keep it the other parameters exactly the same, beta -1 and the low frequency open loop gain of the amplifier at 20. And then we have this one. We plug in this one in our equations here, beta -1. This is also equal to 1. Because AT infinity is equal to 1 minus beta, so this is 1. So we plot it and see what happens. So we start from the loop gain of 0, and then we start adding slowly loop gain. So we have that 3 poles that are start interacting now, and we have the following phenomena. We have the higher frequency pole start to getting far away, higher frequencies. The 2 low frequency poles crash with each other at some frequency, and then split as complex poles, but something very interesting happens here. They are going towards the origin, towards the y-axis. So they are repelled by the third pole. And something also very interesting here is that as they are approaching to the y-axis, the system is becoming unstable. Okay, remember when we talked about the stability in the first lecture? We say that the poles should be in the left hand side of the complex plane in order to be stable, and in this particular case we see that one pole is going to high frequencies and it is real, but the others are complex and then are approaching the y-axis, so they are starting to give instability problem. So we can say that third pole system, it is there is possibility of instability, so it deteriorates the stability. Now let's analyze the presence of zeros in the amplifier transfer function. So we are going to add one 0 here, and we are going to keep with 2 poles and 1 0, and we're going to put a right hand 0. Okay, the right hand 0, it appears in the right side of the complex plane. So I'm going to put a 0 at plus 10 kHz. So let's see what happened in our example. and then we're going to put 2 poles. Okay, so send it to simulation, and then let's see. Oh, I need to comment this. This is sorry, I need to comment this one and then do the single zero, and let's send it again. So 2 poles with a 0, so the 0 is located here, the right hand 0 is located here, and then we have 2 poles. Without the 0, the 2 poles split and they go vertical, but in this case we see that the 0 start to attract the poles, and if the 0 it is in the right hand side, it will start to deteriorate the stability of the system, because now the poles have crossed. In this particular case, with this amount of loop gain, it has already crossed the y-axis, meaning that these poles are unstable. 2 poles are becoming unstable. Now we get the same result using the root locus. The root locus here. The final positions are here. Now what is the main idea here? In MATLAB we can have the root locus directly with this function. The one in the right, which is exactly the same information, it is just extracted by sweeping the loop gain, which is something that we can actually implement in our circuit simulator, as we will see it in the following lecture. So we can actually have the same information that we have in MATLAB, we can have it in Cadence with our circuit simulator. So we see that now these poles are in the right hand side, they are unstable, so this 0 has attracted these poles. So zeros attract poles. That is the conclusion that we can have. Nearby zeros attract poles. Okay, so there is also another example. Now what happens if the 0 it is in the left hand? So we expect that also, since the 0 attract poles, if it are in the left hand, there are 2 possibilities. Let's check both of them. So let's put it 20 kilohertz minus. We comment this one and then we send it. So we have our 0 at minus 20 kilohertz here, and then the poles split and start to become attracted to the 0. Now in this particular case I put the pole at minus 20 kilohertz, but if I had put the pole in the other side close to the origin, then the attraction, the pole will, the 0 will attract it, and then they will go in the other direction. No, they will go to the right instead to the left. So it depends where this 0 is placed. In this case it was placed to the left of both poles, then it will attract to the left. If it had been placed at the right of the 2 poles, the 2 poles will be attracted to the right. Okay, so we can see the resting positions of the poles at the end. So this is my root locus. So zeros attract poles that split. Still, there might be issues with instability. As I mentioned before, I could have put the 0 here and then the trajectories of the if I had put the 0 somewhere here, the trajectories would have been like this instead and can deteriorate the stability. In this particular case, I put the 0 here and then they came in these directions. Okay, so now we know that the negative feedback changed the positions of the poles in the system. It depends on the amount of feedback that we have, on the loop gain that we have, and we actually already had a first approximation of what is going to happen when I put the feedback around an amplifier with some bandwidth. So if this is the bandwidth of my amplifier, it has a low frequency pole. When I apply feedback, then my frequency increases, the pole moves to a higher frequency. Yeah, so we can predict actually what is the bandwidth that I can have. For one pole it is very simple, but when we have several poles it gets a little bit more complicated, but we can do the following analysis about the achievable bandwidth that I can have in a negative feedback system. So for the first one, the first observation is that the denominator of the closed loop gain is the one that provides the frequency behavior of the amplifier, and this is on the assumption that there are no zeros other than the phantom zeros. The phantom zeros, as we saw, they just simplify, so they don't really appear in the they just simplify and they don't appear in the closed loop gain. So let's suppose that this simplifies here, and then under the assumption that this is equal to 1, that means that there are no other zeros around. Under this assumption, then the positions of the poles in the closed loop gain are the ones that are going to define the whole bandwidth of this amplifier. And they can actually be found, the position of the poles can be found analyzing the denominator of the closed loop gain, and that denominator, it is just a polynomial in the Laplace domain. So we will find the position of the poles by calculating the roots, and then when we write this polynomial, we will have some kind of equation that looks like this. Okay, and very interesting, it is the last term. The last term, it is very important for us. The last term, we have that there is a product of the poles, it appears a product of the poles, and then they are multiplied by the loop gain of the system. So these factors are very, very important. The product of the poles and the loop gain start to become very important, because this last factor, it is the one that dominates the bandwidth. Now, we will postulate that in analog integrated circuit design, we want to achieve the maximum possible bandwidth with the minimum power consumption. And what is the maximum achievable bandwidth? We can see it, our amplifier, as a filter with a bandwidth, and there are different kind of filters around. So there is one kind of filter that is interesting for us, that it is the maximally flat magnitude MFM filter, that also known as a Butterworth filter. So this filter is interesting because it has a very flat response at low frequencies, and then it's going to go down. Okay. This characteristic is important because we want flat or as much flat amplification as possible in all the bandwidth of interest. So there are some filters that look like this instead. So we will not want to have filters with ripple because the gain will be different at different frequencies. So this Butterworth filter or maximally flat magnitude filter becomes interesting for us. And so let's study it a little bit. In this filter, we can have this filter with different orders, that is the number of poles that it will have. This filter is designed by distributing the poles over a semicircle on the left hand side of the complex plane. So for a second order filter in red, I will put these poles in this semicircle here. That means that this angle will be minus 45 degrees and this angle will be 45 degrees. And it will be equidistant with the other axis also. This is also going to be 45 degrees, 45 degrees. So I will put these poles at 45 degrees and then they will have the same magnitude. If I have a third order system, then it will be the blue. I will spread the three poles. One will be at 0 degrees and that will be 60 degrees, and this will be 30 degrees. 30 degrees, and there will be 60 degrees, and that will be 30 degrees. That is how I will spread these three poles. If it is a fourth order, then I can do it a little different. I divide the semicircle in 1, 2, 3, 4, 5 parts, and then I spread these poles at 22.5 degrees minus. They will spread. So, and when I have this position of the poles, then I create a maximum flat magnitude amplifier or a Butterworth filter that has it is mostly flat. Okay, so I will postulate that if we can somehow put the poles in these positions, I will maximize the achievable bandwidth of my amplifier. My objective will be to try to put the poles somehow in these positions. If I have two poles in my system, I will try to somehow manipulate those positions so that they end up in the positions of a Butterworth filter of second order. If I have three poles in my system, then I will try to put these three poles in a Butterworth position so that it maximizes the bandwidth. Okay, so the ratio of this semicircle, it is, we will call it Wn. So when we put the poles in Butterworth positions, it happens that this characteristic equation in the denominator, only the highest order terms becomes interesting for us. And then the higher order term, we have that the bandwidth of the system is going to be equal to this ratio of the semicircle, and then we can calculate this one as the n root, n the number of poles. For a two-pole system, it will be a square root, and then there will be the loop gain and the product of the poles. Okay, so it is a combination of loop gain and the pole position, the one that it is going to give me the achievable bandwidth, which it is very, very interesting. So in principle, if I have very high loop gain, I can achieve very high bandwidth. Okay, so a figure of merit here, or first figure of merit here, the loop gain pulse product, and it is something that we're going to have a separate lecture because we really need to study this loop gain pulse products very deep. It is what it basically gives us complete design methodology. We're going to define this at LP, and it is going to be equal to the complete loop gain and the product of the pulse. And then, yeah, our bandwidth can be expressed as a n root of the loop gain pole products. So now let's take back our previous example in which we have two poles located at 1 kilohertz and 5 kilohertz. The same thing, we have a open loop gain amplifier with a gain of 20. Beta we selected -1. And now we are going to place a phantom zero in A beta by adding a pole to the transfer function. Okay, so the asymptotic gain, we add the pole to the asymptotic gain. The asymptotic gain, it will look like this. A beta null, the low frequency loop gain has not changed, it's the same. But now what we have is that the loop gain introduces a zero, because we have said before that this pole in the asymptotic gain becomes always a zero in the loop gain, so it will appear here. Now when we plug in all these terms in the closed loop gain equation, we have the following parts. We have this part that has not changed. The numerator and denominator, the phantom zero, it is going to be simplified, so it will disappear from the numerator and denominator, and then we will only have the characteristic equation that we have here, in which we have different terms of the polynomial. Okay, and again we see almost directly there is terms that depends on the P1 and P2. There are terms that depend also here on the loop gain. So in a second order Butterworth filter of MFM filter, we have that the closed loop gain for that filter takes the following form here, like this. So now what we're going to do is we're going to compare, and then we just change the color to green. So this one, it is going to be here, this one it has to be here, and this one it is going to be here. So my task will be to move this part of the equation to a Butterworth filter so that my amplifier can have a maximum bandwidth. Okay, so we continue. So how do we force the positions of the poles of our system in Butterworth positions? So as we saw before, we have the positions of the poles being affected by the loop gain and the position of the phantom zero. So for our system we have the following characteristic equation here. So we need to match this one, has to be equal to this part, and we need to make sure that this part is equal to this one here. That is easily done. Just we need to equalize these equations and then find what are the values. So for the quadratic term, we have that 1 minus the loop gain, product of the poles has to be equal to Wn. Wn is the ratio of the semicircle in the Butterworth filter. So typically A beta null it is very large, and then we just can omit this one, and then we have that we can approximate omega n squared to this value, and then from what we saw before, the LP is equal to the LP it is equal to 1 minus I beta null, and the product of the poles so we will actually have here that when we take the square root of this, we will have that will be equal to the omega n, to the maximum achievable bandwidth. So again, in the Butterworth filter, we have that this distance is omega n. That will be the maximum achievable bandwidth. So we can calculate with, in this particular case, the second order, it will be the square root of LP. Okay, for the linear term is P1 plus P2 minus, and here we have this term here, that it is equal to omega n square. It's the term that we have here. It is almost the same, but without the 1. It's just approximately the same. So we can replace it here, and then we have this part here, and this has to be in the Butterworth filter equal to minus the square root of 2 omega n. Then we can find the position of the phantom zero. The phantom zero should be located in this position, okay, with this equation. And the only condition is that it has to be negative. As we mentioned before, we showed before, the position of the phantom zero should be negative to be effective. And for that to be true, then we have to make sure that this is more negative than this part. So that the whole expression becomes negative. So again, omega n we can estimate rather quickly. Omega n is going to be equal to the square root of 1 minus I beta null. In this particular case, it's only 2 poles, P1, P2. We estimate very quickly. If the loop gain it is very large, this become approximately A beta null, and then I take the absolute value because beta null it is negative. Beta is always negative for us, and it will take just this value, and then I have my expression for the phantom zero here, that it is going to be equal to minus Pn square P1 P2 plus square root plus square root of 2 omega n. Okay, and those are my equations, and this is my condition. So I should always check this condition before I try to put the poles in Butterworth positions. So we come back to our example. We have 2 poles here. We have that the asymptotic gain is equal to 1, beta is equal to 1, the gain of the amplifier is 20, the open loop gain, and the transfer function of the amplifier including the 2 poles is the following here. Low frequency loop gain is minus 20, And then I can already do a first calculation of the achievable bandwidth. My achievable bandwidth is going to be equal to the square root of the LP, the loop gain bandwidth product, and that gives me 10 kilohertz. That is the achievable bandwidth if I can put these poles in Butterworth positions, if I can manipulate the position of these two poles in Butterworth positions. So let's see. The original positions is this one starts in -1, this is -1 kilohertz, and this one starts in 5 kilohertz minus 5 kilohertz minus. Okay, they start in this position, and then I do a very quick check. The sum of both poles, it is 6 kilohertz. I have to check that it is lower than the square root of 2 multiplied by 10.25 kilohertz, that is 14 kilohertz. That is correct. That means that I can put a pole, I can put a phantom zero that can manipulate the poles in Butterworth positions, and then I do the calculation for zeta using my equation here. Using my equation here, and then that gives me a value of minus 12.36 kilohertz. So that will be, I can put the zero here. So after adding zeta, we put the poles in Butterworth position. So let's take a look to MATLAB when we do that very quickly. We have MATLAB script that it is ready for that. So this MATLAB script basically calculate the achievable bandwidth, calculate the position of the zero, and then it plots the rod locus. So let's run it. We see at the beginning with the start increasing the loop gain, the poles start moving, they crash around 3 kilohertz, and then they start to become manipulated by the phantom zero, and then slowly they are starting to go to their final positions that are Butterworth positions. And then when we achieve this, our system behave like a Butterworth filter with a maximally flat amplification in frequency. So okay, so now it is finished, and then we can see that positions around 7 kilohertz. Okay, we got our final positions at around 7 kilohertz, and then according to our calculation, then the achievable bandwidth was 10.25 kilohertz, and then we have that our positions here are -7. It's around -7.5 and 7.5 plus minus. Okay, which is it is exactly what it is supposed to be, because the distance is from the origin. So this vector should be exactly 10 kilohertz in magnitude. Okay, so this is very interesting, very important. This kind of compensation is the thing that we are going to be doing. We will show other compensation techniques to stabilize circuits, but this is very powerful. It works very well for 2 poles. It is possible to do it also with 3 poles, a little more complicated, but for higher order systems it is not so easy to manipulate so many poles. But typically in analog circuit design, we will have 2 dominant poles that we can manipulate, maximum 3. Okay, that is all for today.